Good morning, friends. I, Dr. Devis Bandel, Associate Professor, Suresh Gyan Vihar University, that is accredited by NAC A grade. I will discuss about how to delete a node from binary search tree. Now I am sharing my PPTs. You know, I hope you can see my PPT. So today I will discuss about search a given key in a BST. Okay, means how to search a key value from a BST. And also in this lecture, I will discuss about how to delete a node, how to delete a given key from your BST. And BST about if we will discuss about the BST, your BST is that your binary search tree. And if we will discuss about the object and outcome of your DSA, the objective of DSA is that to emphasize the concept of your algorithm, emphasize the concept of your stack, emphasize the concept of your queue, emphasize the concept of tree searching and your sorting. And after studying this subject, student will learn about how to write the algorithm, how to find the complexity, and also a student will able to all searching technique, all sorting technique, and also student will able to concept of a graph and concept of your tree. And in this lecture, I will discuss about search a given key in BST. And also in this lecture I will give overview of how to delete a node from a BST and how to delete a node in your how to insert a node in your BST. And in this lecture, I mainly focus on that how to search a given key from a BST. And in this lecture, during this lecture, I will cover so many topics like that. First of all, I will discuss about object and outcome of this lecture. And also I will discuss about overview of a binary search tree, how to represent a binary search tree. And also I will give the overview of your basic operations of your BST, and mainly focus in this lecture on a search a given key in BST and how to implement in any other programming language. And after this lecture I will discuss about the some questions which are related from this lecture. And first of all I will discuss about the object and outcome of this lecture. And I had already discussed about the object and outcome of your DSA. And the BST is the main concept of your data structure and algorithm. And in your BST, how to search a given key. That is the main important things of your binary search tree. That's why I will discuss about the object and outcome of this lecture. If we will discuss about the object of this lecture to understand the concept of your search a node in a BST. And if we will discuss about the outcome of this lecture to be able the search node in a binary search tree. So your this is the your object and outcome of this lecture. And I will discuss about the binary search tree. And binary search tree is the one of the type of your tree. And here we are discussing about binary search tree. So a BST is a tree in which your all the nodes follow the below mentioned property. Your first property is that the value of the key of left subtree is less than the value of a parent node key. This is the first property of your binary search tree. And the value of the key of the right subtree is greater than or equal to the value of its parent root node key. That is the second property of your binary search tree. And your BST divide all the subtree into two segments, the left subtree and into your right subtree. Mainly focus in your binary search tree. In your binary search tree, your left subtree value is always less than from your root key value, and your right subtree value is always greater than or equal to from the root value. And you can define you can define the relationship between parent node, between left subtree and your right subtree through a mathematical expression like that. Left subtree value is less than root node less than equal to right subtree value, because as per I had told, in a binary search tree, your left subtree value is minimum from the root value, and your right subtree value is greater than or equal to from the root value. Okay, that's why you can say that your mathematical expression is that left subtree less than node key less than equal to right subtree. And BST is a collection of a node arranged in a way where the maintain the BST property. Here I had talked about the BST property. Your BST properties are your left subtree value should be less than from your root key value, and your right subtree value is greater than or equal to from your root value. And that's why you can say that your left subtree value, your root value, and your right subtree value are in a ascending order, because as per I had told, your left subtree value is less than from your root value, and your root key value is less than equal to from your right subtree value. That's why I am saying BST is a collection of your node arranged in a way where they maintain the BST properties. Each node has a key and an associate value. While searching, the desired key is compared to the key in your BST, and if found, the associate value is retrieved. Okay, and you know representation of a BST. When you will represent the BST, that is your binary search tree, so always you will follow the property as per I had told. Okay, in this image, in this slide, you can see that your root key value is 27. Okay, and your 14 is your left subtree value, and your 14 is less than from your 27. That is the property of your BS tree. That is your left subtree value all should be less than from your root key value, and your 35, your sorry 35 is your right subtree value, and your 35 is greater than from your 27 as per your BST property. Your BST property, as per your BST property, your right subtree value is greater than from your root key value. And in your level second, your level will start from your top to down. Your level will start from your zero, zero. First level is your zero, second level is your one, and third level is your two. So here I had mentioned the some nodes at your level zero, level one, and level two. If people talk about the level two, so in your level two, 10 is your left subtree value, that is less than from your 14, and your 19 is your right tree subtree value, that is greater than from your 14 as per your BST property. And your 31 is less than from your 35, that is the BST property. And also 42 is greater than from your 35. And here I have to maintain the all BST property, and I have to define a binary search tree as per the properties of your BST. BST like binary search tree. And you know, the main focus of this lecture, we will discuss about the how to search a key value in your BST. If we are discussing about a search a key value in your BST, you should know about the what is the BST, how to represent the BST, what are the basic operations of your BST. Okay, so now I am discussing about the all basic operations of your BST. You know These are the some basic operations of your BST, like your search, insert, pre-order traversal, in-order traversal, and your post-order traversal. These are the all basic operations of your BST. And in this lecture, I will discuss about the search operation in depth. So first of all, your search operation. Search means when you will search the any node in your BST. When you will search the given key in your BST, that is your search operation. And if we will talk about the insert operation, so insert, through the name you can understand. Insert means when you will insert a node in your BST, when you will insert a node in your binary search tree. So that is your insert operation. And after that, pre-order traversal, in-order traversal, post-order traversal. I had also discussed about in my past lecture about your pre-order traversal, in-order traversal, and your post-order traversal. But here I will give the overview of your three operations, like your pre-order, in-order, and your post-order. Your pre-order traversal, when you will traverse the all items in your pre-order fashion. Okay. And if we will talk about the post-order traversal, when you will traverse the all node in your pre-order fashion. If we will talk about the post-order operation, so when you will traverse the all node of your tree in your post-order fashion, this is your post-order traversal. Okay, so these are the all operations of your BST. First is your search operation, insert operation, pre-order, post-order, and your in-order traversal. And now, if you will insert the any node in your BST, if you will delete the any node from your BST, if you will search the any key value in your BST, so for these operations, you should require a how to create a node. If you are having node, so means you can insert the node in your BST, you can delete the node from your BST, and you can search a node from your BST. So you should know how to create a node. So when you will define a node, your node will be defined through the structure, and your struct is the keyword of your structure. And in which you will take the data, your node having the data, and also you will take the two pointer. Your first pointer is for the left subtree, and second pointer is for the right subtree. That's why in this slide, for a creation or node, I have taken a data of integer type, and also I had taken the two pointer. First pointer is your left child pointer, and second is your right child pointer. You can see here. And now, first I am giving the overview of your insert operation. When I had talked about in my past lecture about your stack, about your queue, about your linked list. Okay, so your insert operation, you can insert the item in your stack, you can insert the item in your queue, you can insert a key value in your BST. Okay, so that's why you can better understand about your insert operation in a simply manner. You know, whenever you will insert a key, whenever you will insert a node, first you will locate the right position. Okay, and always you will start from the root position. Always you are searching, either you are inserting, either you are deleting, either you are searching. Always your searching will start from your root value. Okay, and if the data is less than the key value, if your inserting data value is less than from your root value, always you will choose the path of your left subtree. And if your inserting data is greater than from your root value or equal to from your root value, so you will choose the right path of your subtree. That's why I am saying, if the data is less than the key value, search for the empty location in the left subtree and insert the data. Either search the empty location in the right subtree and insert the data. This is the main key point, main focus on this point. If your inserting key value is less than from your root value, so you will choose from the left subtree path and you will insert the data. And if your inserting key value is greater than from your root value, you will choose the right subtree path and you will insert the data. And now, you can write the algorithm for the inserting node. Algorithm, as per I had told many times, algorithm is just instructions, and your all instructions should be in your sequential manner, should be in your step by step. That is your algorithm. In this algorithm, if your root equal to null, so return the new node to the calling function. Calling function means your insert node. And if your data less than your key, call the inserting function, right, and assign the return value to the right. And if your data is greater than your key, call the insert function and assign the return value in your left. And finally, return the original root pointer to the calling function. So that is the algorithm of your inserting function when you will insert a key value in your BST. Okay, the main objective of this lecture is not a inserting, not a deleting. The main objective of this lecture, how to search the node from BST. Okay, that's why I'm not going in detail. And if the tree is your empty, then the new node in the root, obviously if you are inserting a node in your BST, if you are inserting a node in your BST and suppose your tree is blank, means there is no any root node, there is no any left subtree, and there is no any right subtree, means your tree is totally blank. Okay, so after inserting the new node, you will return the new node in the root, because your root will be insert in your root node, because your tree is your empty. And if your tree is empty, if your tree is empty, means there is no any left subtree, there is no any right subtree, and there is no any root. And when you will insert the node, so your node will be insert in your root key value. And if we will return the new node, if your root equal to the null and return the get new node value. and we should find the correct place in the right subtree and insert the new node. Okay, and we should find the correct place in the left subtree and insert the new node. You know, as per the algorithm, if your inserting node key value is less than from your root node, so you will select from the left subtree path and you will insert the node. And if your inserting node key value is greater than or equal to from a root value, that is, you will choose the from right subtree part and you will insert the value. And if your this is the implementation, like it will handle two cases: prevent the duplicate nodes in the tree. Okay, if a key equal to the value, it will straight away return the address of the root node. And second, after the insertion, it will return the original unchanged root's address. And after that, I will discuss about the example of searching operation. Your searching is the one of the operation of your BST, and the main objective of this lecture, we will discuss about the searching operation of your BST. You know, First of all, as per I had told, always you will start from the root. If you are searching any node, if you are searching any node value from a BST, always your searching will start from your root node. Okay, and in your second step, compare the when you will compare the search element from the root. As per I had told, you will start from the root and compare the searching key value from your root value. If you are less than from your root, then recurse the left subtree, else recurse the right. Okay, and if the element to search in found anywhere, return true, otherwise return to false. Means, you can see that is the algorithm of your searching operation. Algorithm of your searching operations means your searching will start from the root. As per I had told, your searching will start from the root, as per I had told. And if your And your your you have taken the two pointer, one for the left pointer and one for the right pointer. And after that, you will create a new node pointer, and your new node will be assigned to your node, and your key will assign, and your left and your right pointer. And after that, recursive function to insert key in your BST. That is the function for a insert key. If your root is null, create a new node and return it. Okay. Suppose if your root is null, means suppose your tree is your empty, so your new node will be a root node. So you can see here. And if the given key is less than from a root node, you will recurse the left subtree as per I had told. And if your given key is greater than from your root node, you will recurse the right subtree as per I had told. You can implement here. And now this is the function for a search a node. Okay, so in your search node, if the key is not present in the key, so your root will equal to the null pointer. Suppose if you are finding any value in your BST and your finding value is not present in your tree, so your root is equal to the null pointer, and you will display a message, key is not found. And return. And if your data is equal to the key, so your parent is equal to the null pointer and these node with the key, and your prince. And if your key is less than your parent, the given key is left node of the node. Okay, as per I had told, your searching will start from your root node. Okay. And if you are suppose your root node, your key is not present in the key, so your root node will point to the null pointer. And if your key is less than from your root node, so you will follow the left subtree. And if your key is greater than from your root node, you will follow the right subtree. So you can see here. And after that, if the given key is less than, root node recurs for the subtree as per I had told, otherwise recurs for the right subtree. And if your key is less than from your root, return the search operation. Okay, and after that you will apply a main function, because before a main function you have to made a function for a insert key, for a delete, and for your searching. And after the main function, you will taken the value like your 15, 10, 20, 8, 12, 16, and or 25. Okay, and you will call the all functions. This is the implementation of your search a key value from a BST, insert a key value from your BST. You can see here. And this is the tree. And in this tree, I had followed the all properties of your BST. You can see here. Suppose your 7, suppose your 7 value. Okay, so your 6 is less than from your 7, and that's why your 6 is the root value. And your 4 is less than from your 6. That's why that this is the left subtree value, and that is the less than from your 6. And here example of your insert key. When you will insert a node key value in your BST, a new key always inside your new key value will be inserted at your leaf node. you know if you will talk about the leaf node are those nodes who have no any branches. They say that is your leaf node, and we start searching a key from the root until hit a leaf node. And once a leaf node is found, the you know, in this pre-order traversal and your post-order traversal and your in-order traversal. If we will talk about the in-order traversal, your in-order traversal, first of all, your in-order traversal, first of all, you will traverse the left subtree. After that, you will traverse the root node. After that, you will traverse the right subtree. This is your in-order traversal. Means you will traverse the all nodes in your in-order fashion. Okay, and if we will talk about the pre-order traversal, in your pre-order traversal, your first of all you will visit the root node. After that you will visit the left subtree. After that you will visit the right subtree. This is your pre-order traversal. Means in your pre-order traversal you will traverse the all nodes in your pre-order fashion. You can see here. Here, first of all, you will traverse the A node. After that, you will traverse the B node. After that, you will traverse the C node. And if here you will traverse the in-order traversal, so first of all, you will traverse the B node. After that, A. After that, your C. And you know here is path as per your pre-order traversal, and this is the algorithm as per your pre-order. First of all you will visit the root node. After that you will traverse the left subtree. After that you will traverse the right subtree. And your post order traversal, in this traversal method the root node is visited last, hence the name. First we traverse the left subtree, then the right subtree, and finally you will traverse the root node. And here if you will apply the post order traversal, in your post order traversal, first of all you will traverse the left subtree. After that you will traverse the right subtree, and after that you will traverse the root node. Means your first you will traverse the B node. After that C node. After that your A node. And here if you will traverse the in order, so if you will traverse the in order fashion, first of all you will traverse the B node. After that A node. After that C node. And you can see here, this is the path, and this is the algorithm for your post-order traversal. Recursively traverse the left subtree. After that recursively traverse the right subtree. After that you will visit the root node. And you can see here from this slide, this is the example. And here I had to apply the all ordered fashion, like your in order fashion, like your pre-order fashion, and like your post-order fashion. And this is the tree. And here I had maintained the all properties of your BST as per your left subtree is less than. Okay. And here in order traversal, here is your in order traversal. Okay. And this is the another question as per I had discussed. This is your level order traversal, you can see here. And in this another question, what is the space complexity of the in order traversal in the recursive fashion? D is the tree depth and N is the number of your nodes. So your first option is that your one, second option is that your n log d, and d. So your answer will be the D. Your space complexity of the in order traversal in the recursive fashion. So D is the tree depth and N is the number of your nodes. That's why your answer will be your D. And what is the time complexity of the level order traversal? Your first is that your 1, second is that your n, third is that your log n, and fourth that is your n log n. So your answer will be your B, that is your n. The time complexity of the level order traversal is that your n. And now another question is that which of the following graph traversal closely imitates level or a traversal of a binary tree? Depth first search, breadth first search, and your binary search. Breadth first search graph traversal closely imitates level or a traversal of a binary tree. That's why your answer will be your B answer. That is your breadth first search. And in a binary search tree, which of the following traversal would print the numbers in the ascending order? Level order traversal, pre-order traversal, post-order traversal, and your in-order traversal. So in your binary search tree, always in order traversal will print the numbers your in ascending order. Because your in-order traversal, first of all, you will traverse the left subnode. After that, you will first of all you will traverse the left subtree. After that, you will traverse the root node. After that, you will traverse the right subtree. That's why your answer will be your in-order traversal. And the data structure used in standard implementation of breadth first searches: stack, queue, linked list, and tree. So your answer will be your B, that is your queue. Because in a breadth first search, data structure used in a standard implementation, in standard implementation of breadth first search is a queue, not a stack, not a linked list, and not a tree. And the breadth first search traversal of a graph will result into linked list, tree, graph with back edges, and your array. So the breadth first search traversal of a graph will result into a tree. And a person want to visit some places. He start from a vertex and then want to visit every places connected to this vertex and so on. What algorithm he should use? Every time he should use the breadth first search, because in a breadth first search you will start from a vertex and then want to visit the every place connected to this vertex and so on. That's why we will use the breadth first search algorithm. And another question is that which of the following is not an application of a breadth first search? Finding shortest path between the two nodes, and finding bipartitionness of a graph, GPS navigation system, and your pathfinding. Your A option, B option, and C option all are the application of your breadth first search. But your pathfinding is not an application of your breadth first search. And another question regarding implementation of breadth first search using queue: what is the maximum distance between two nodes present in the queue? Can be anything, zero, at most one, and insufficient information. Your answer will be your one. And in the last question, which are related from this lecture, in BFS, how many times a node is visited? In your BFS, you will node visited not a once, not a twice. You will visit the equivalent to number of integrity of the node and your thrice. I hope you have understood about this lecture. And in this lecture, I had discussed about uh, how to search a node from a BST, means searching a key value in your BST. I am very much confident you have understood about this in a better manner. Thank you.